So in this video we are going to discuss Huffman encoding. First we'll define the problem and then give a efficient greedy algorithm for the problem. So in the Huffman encoding you are given a text containing alphabets. In this example, let's assume that the alphabets are A, B, C, D, E and F, and we are given the frequencies. In other words, given a long text out of 100 characters, on average A appears 24 times, B appears 25 times, and D appears 6 times, and so on. Given the frequency of these elements, alphabets in the text, we want to do an encoding into binary. So we want to encode this into binary so that the length after we encode it is minimum. Let's look at one equal length encoding scheme where instead of A I can write 000 and B I can write 001 and so on. If I want to include, whenever there is an A coming, I have to just write 001, and whenever D comes I have to write 011. With this scheme you can see that every text containing A, B, C, D, E, F can be converted into binary. But what happens is that since each of these characters is encoded with a binary string of length 3, so if you are starting with a text with n number of elements, after you encode into binary, this will have 3 into n is the length. So average bit per character in this case is 3. So is there an alternative way of encoding this? Probably with variable encoding scheme, so that on average the number of bits per character that we use is minimum. Let's look at one possible solution. I can encode with A as 00, B can be encoded with 10, and C is 110, D is 010, and E is 111, and F is 011. With this encoding scheme, you see that the first two characters which appear more frequently have been given a encoding of length 2, and the remaining all have been given a encoding of length 3. So that means that A and B happen very frequently, so we want to encode it with a smaller length code, and so remaining characters, all of them are given the same length code, which is 3. So if you use this, you know that the first two happens with probability 49, so the rest of the thing should happen with probability 51. So the average bit per character in this case will be 0.49 into 2 plus 0.551 into 3, because if you take A and B, the total probability of that will be 49%, and the length of the code is 2, and the remaining C, D, F and E, they can only appear with probability 0.51, and the length of the code is 3. So average turns out to be 2.51, which is much better than 3. If you look at a string of length 1 million, then if you use a length 3 code, then you have to, when you encode it, you get 3 into 1 million. But in this case, what happens is that if you want to encode a string of length 1 million, so after you encode into binary, the length of the code will be about 2.5 million, right, instead of 3. So the improvement is over 2.51 over compared to 3. But how do we get this encoding scheme? Once you get this encoding scheme, you know that every time A appears, you can just replace with 00, and every time when 00 comes, you know that this is being decoded into A. So this is where the Huffman encoding scheme comes into picture. Let's look at a greedy algorithm to given these frequencies. The greedy algorithm will give us the encoding scheme. First we start with all the alphabets in the leaf nodes. You can define them as leaf nodes in the binary tree, and I take the minimum 2 priorities. The minimum 2 priorities in this case happens to be 6 and 14. I create a node and make one of them as the left child and the other one as the right child, and I add up the frequencies. So now among so I now I consider these two, instead of the, I delete these two nodes and I'll consider this node with the 20 as the in the input. So I will consider 24, 25, Other thing that we are going to consider 16, and once you merge these two frequencies, I get the frequency as 20 and 15. So among the number 24, 25, 16, 15 and 20, I pick the minimum 2. The minimum 2 happens to be 16 and 15. So I create a node and make one of them as the left child and the other one as the right child. Now when I have to continue this, now the numbers that I have to consider is 24, 25 and 31 and 20. The minimum two are 20 and 24 is the minimum. So if I make one node and make A as the left child of 44 and the right child is 20, right? So the remaining two are the other two things that we had is when I add up this, this we get 24, and so before this we had 25 and 31. The next minimum is 25 and 31. I combine them and make it as a node. So this 25 plus 31 is 56. Now only 44 and 56 is left. So what I do is that I combine them as make a tree, and you know that the total is 100. So given the frequency of different alphabets, let's say that algorithmically we started with n different nodes in the heap, and the priority of each of these elements is the frequencies. What we did is that we deleted the minimum 2 frequency nodes from the heap, and then we added the frequency of these two nodes and created one more node and made one of the child as the one of the child that we deleted and the other one as the other child that we deleted, and this 20 was inserted, a new node was created, and this new node was inserted into the minimum heap with priority as 20. So next time you apply the same algorithm, you take the minimum 2 elements from the heap, that happens to be 16 and 15. You delete these two nodes from the heap, you create a new node, make the deleted nodes as the children of this, and add this node back to the heap with priority, which is the sum of the priority of the nodes that you just deleted. So 16 and 15 is deleted and 31 is added into the heap. And next we again create a node, and the next minimum that we are going to delete is 20 and 24. When we deleted 20 and 24, we create a node and write the priority as 44, and the one of the nodes that we deleted becomes the left child, and the other node that we deleted becomes 24. Next we are going to delete 25 and 31, and so this is added to 56, and then we again, there are only two nodes that are left. You delete these two nodes and create a node and write the priority as some of these two nodes and make them as the children of the new node that you created. So this is a simple algorithm. So initially you build a heap with all the n nodes, and in each step you delete two nodes and add one node with the priority as the sum of the priority of the two nodes that you deleted, and create a node and make the two children, two nodes that you deleted as the children of the node that you created. Since every time I am going to delete one node, two nodes and add one node, in every iteration the total number of nodes will decrease by 1. In n minus 1 iterations, this algorithm will terminate. Note that in each of these iterations I am deleting two nodes and adding one node, so both of them will take order log n time. In order n log n time, we can create this tree. And you also notice that the number of leaf nodes, all the alphabets are in the leaf nodes, and the number of leaf nodes is exactly equal to n. And so we also know that since it is a full binary tree, we know that the number of internal nodes will be exactly equal to 1 less than the number of leaf nodes. So the total number of nodes in the tree will be n plus n minus 1. In other words, there will be exactly n number of leaf nodes and n minus 1 internal nodes. So now it's easy to come up with the binary encoding for the each of these alphabets. So what you do is that you start traversing the tree from the root node. Every time when you take a left turn, you write a 0. Every time when you take a right turn, you write 1. For example, if I have to reach A, first I start from here, I go left, and then I go left again. So the encoding for A is 0 0, right? So encoding for B is the path from the root node. First you go to the right and then come to the left. So the encoding for B is 1 0. The encoding for C is first you take a right child, then again a right child, and again a left turn. So the encoding for C is 1 1 0. Encoding for D is first you take a left turn, then you take a right turn, again you come to the left. So this will be the encoding for D will be 1 0 1 again 0. Now if you have to come to E, first you have to start with the root node, take a right turn, then take a right turn, and then again take a right turn. So this will be encoding for E will be 1 1 1, and for the encoding for F will be 0 1 1, right? So you start following the path from the root node to the leaf node. If you take a left turn, right 0. If you take a right turn, right 1, right? So that's all will give you the encoding for each of these alphabets. So if you have to encode A, B, C, D, then you have to just replace A with the encoding of A, and so B with the encoding of B, and so on. But how do we do the decoding, right? So if you are given a string in the binary, how will you map it back to 0? The once you have this Huffman tree, it's always easy to decode also. For example, if I want to decode this, what I do is that I start with 0. Say I start my traversal from the root node. If I get a 0, then I go to the left. Then if I get a 1, I'll go to the right. Then if I get a 0 again, I'll come to the left. So when I reach the leaf node, my traversal stops. There is a break here. I have given a gap because I have reached the leaf node. So the node that I have at the leaf node now is D. I report that 0 1 0 corresponds to D. Now again I start with the next one. So next one I start traversing from the root node. So 1 I have to go to the right. Again 1 I go to the right. Again 0 I come to the left. So the character that I get is C. Next I have to go to 1, then 0. So 1 0 corresponds to B. So the moment I reach a leaf node, I have written a gap here. That means that this is corresponds. So that's where my traversal ends, and again I start traversing from the root node. In general, you are just given the binary encoding. When you are given the binary encoding, just follow the path. Once you reach the leaf node, you again start traversing from that alphabet corresponding to the leaf node, and then again start traversing from the root node. So for example, if I have to 1 1 1 corresponds to, I take a right turn, then again I take a right turn, and again take a right turn. This is corresponds to A. If I see 0 0, I have to go to the left, and then again go to the left. I reach the leaf node again. So that is where the encoding ends. So whether a encoding ends or not will depend on whether you are in the internal node or in the leaf node. You start traversing from the root node till you reach the leaf node. Once you reach the leaf node, note down the character corresponding to that leaf node, and again you start traversing from the start reading the next character and start your traversal from the root node, right? So this gives a simple algorithm to convert the binary encoding into the alphabet set, and encoding the alphabet set back to the binary. As we said, since we know that the encoding for A is 0 0, you straight away replace A with 0 0, right? So this tree can be used for both encoding and decoding, and given the frequency of the alphabets, you can construct this tree in order n log n. And encoding, you don't have to traverse the tree, you have to just replace the character with the encodings. And if you want to decode, you can use this tree to decode the given binary string into the set of characters that are given to us. So in this video we have seen what is Huffman encoding, how do we do it. The main idea here is that when the frequency of the characters is very small, It's okay if the encoding is encoding length is very high, but if the frequency is very big, we want the encoding length to be as small as possible. So that's precisely what we did, is that we started with frequencies which are very low, and added them and created a new node. This essentially means that when you start traversing from the root node, the length of the path to this leaf node will be higher, right? So that's the main idea. If the frequency is lower, then we are okay with the length of the path to be higher, but we want the length to be smaller if the frequency is very high. In this sense, this algorithm is a greedy algorithm. There is a proof that the whatever algorithm that we considered in fact will give us the minimum length encoding, but we will not get into the proof of this in this video. But we want to emphasize that this cannot be modeled as a metroid. So in the previous class, we have seen that some of the we defined what is a metroid problem, and we have said that some of the greedy problems can be characterized as a metroid problem. But this is one such. It's not necessary that every greedy algorithm can be characterized as metroid. The Huffman encoding is one such example where the greedy algorithm works correctly, but this need not be a metroid. So if you can model the a problem as metroid, certainly the greedy algorithm and the metroid will give us the optimum, but the converse need not be true. It's not necessary that every problem for which greedy gives the optimum need not be modeled as metroid. The Huffman encoding is one such greedy algorithm which cannot be characterized as metroid. um, that's all we have in this video. Take a break and come back to the next class.